After a detailed discussion on nuclear cell model, now in nuclear physics we are going to start a new chapter, nuclear decay. In fact, in this chapter, nuclear decay, mainly we will study three types of decay process, and those processes are alpha decay, beta decay and gamma decay. Actually, this chapter is very important for the students of MSc level, BSc level, and also preparing for the different competitive examinations like NET, JRF, and the civil services examinations. In civil service examination, you can see the past year question that particularly the questions are asked regarding the beta decay process and the gamma decay process. So this chapter will be very helpful for those students. Now, before starting a particular decay process, I would like to say something about this nuclear decay process. You know, you have studied earlier that our nucleus may be stable or it may be unstable. In fact, a nucleus is stable or unstable, that depends on the combination or the ratio of the number of neutron and the number of proton. In fact, in general, not very strictly, but in general you can say that if the number of neutron over the number of proton, here n represents the number of neutrons present in a nucleus and z represents the number of protons in the nucleus. If this ratio n over z is less or equal to 1.5, then it is seen that most of the nuclei which have this ratio less or equal to 1.5, they are mostly stable, although there are some exceptions, because in nuclear physics you cannot say any strict rule. But most of the nuclei which have this ratio less or equal to 1.5, they are stable. But when this ratio actually exceeds 1.5, then the nuclei are unstable. So you can say that a proper combination of the number of neutron and the number of proton actually is a parameter to determine that the nucleus will be stable or unstable. But in nature, there are several nuclei in which this proper combination of n and z, which is required for a stable nucleus, are not found. It means there are nuclei in which case the ratio of n over z is greater than 1.5. Such nuclei exist naturally, and these nuclei can be prepared artificially in the laboratory. And these nuclei are somewhat unstable. But an unstable nucleus has always a tendency to get stability, and for this the nuclei suffer actually different decay process. So why this decay process takes place? The basic reason behind this nuclear decay process is what? This is actually just a tendency of nucleus to be stable. Every nucleus tends towards stability, and for this our unstable nuclei suffer different type of decay processes. Among these different processes, mainly there are two decay processes in which a nucleus is changed into another stable nucleus. A nucleus which is unstable, that is transformed into another stable nucleus, and those two important processes are alpha decay and beta decay. It means the nucleus emits alpha particle and transform into another nucleus which is in fact stable. Similarly, a nucleus which is unstable emits a beta particle, and then a new nucleus is formed which is called daughter nucleus, which will be stable. In fact, apart from these two decay processes, that is alpha decay and beta decay, there is also a very important decay process that is called gamma decay. But you should note that during this gamma decay process, no new nucleus is formed. During alpha decay, we get a new nucleus which is stable. During beta decay, again you get a new nucleus which is called daughter nucleus, which is stable. But during gamma decay, when a nucleus suffers gamma decay, no new nucleus is formed. Only the state of energy of the nucleus gets changed. In fact, when an unstable nucleus suffers either alpha decay or beta decay, the resulting daughter nucleus is actually found in some excited state. That is, the energy state of the daughter nucleus is in fact larger than the energy of its ground state. So if due to the alpha decay process or due to the beta decay process a nucleus is obtained and that nucleus is in an excited state, then this nucleus in excited state is unstable and it transforms into or transits into a lower energy state. Let us see here. If you consider that a nucleus is in this excited state, say this is an excited state, and in this state this nucleus has been obtained due to the gamma decay process or beta decay process, then this nucleus emits energy in the form of gamma photon, and then releasing that amount of energy, this nucleus transits into a lower energy level. This energy level may be also an excited state, but compared with this first state, the energy of this second state will be smaller. And in fact, finally, our nucleus returns back into the ground state. So, in gamma decay process, the identity of the nucleus does not change, neither its charge number, that is the number of proton, nor its mass number gets changed. Only the energy state of the nucleus is changed. So gamma decay process is something different from the alpha decay process and the beta decay process. Okay. And as I have told you earlier that in this chapter on nuclear decay, we will discuss in very detail all these three decay processes, that is alpha decay process, beta decay process and gamma decay process. In the syllabus of some of the universities, this gamma decay process is not to be studied, but in several other universities you have to study all these three processes, and particularly in civil services examinations we have to study all these three processes, that is alpha decay process, beta decay process and the gamma decay process. So in this lecture, in this first lecture on this nuclear decay process, I am going to start to deal with the alpha decay process. In fact, in this first lecture, we will see only the elementary concept of alpha decay process. But in the forthcoming lecture, we will see a proper theory which is known as Gamow theory of alpha decay, by which you can explain this decay process by quantum mechanics. We will see those concepts in the forthcoming lecture. But in this first elementary lecture, we will only see some of the outlines of this alpha decay process. So let us start to know what is this alpha decay process, when it takes place, and what type of daughter nuclei we will get after this decay process, and what will be the Q value of this nuclear process. We will see these things in this elementary lecture. First of all, I would like to explain that what is an alpha particle. Alpha particle, in fact, you can simply say that an alpha particle is nothing. This is simply the nucleus of 2He4 atom. It means, you know, the 2He4 atom has 2 protons, 2 neutrons and 2 electrons. If by any mechanism you remove all those 2 electrons from this neutral atom of helium, then you get alpha particle. After emitting these 2 electrons, there will remain only the nucleus of He4, and that nucleus of He4 is called alpha particle. Since this is just the nucleus of He4, and you know in the nucleus of He4 there are 2 protons, so actually the charge of the alpha particle Q is plus 2e, where E is actually the charge of a proton. This is a very elementary fact, and you better know it, and as I hope. Now, what type of nuclei will suffer alpha decay? First of all, we will see. You should note here that all those nuclei having mass number greater than 210 will suffer actually the alpha decay process. But the question arises, why a nucleus which has a larger mass number or the nuclei which are heavier, that suffers alpha decay? Why? Why this decay process takes place only in case of the nuclei having a larger mass number, particularly greater than 210? First of all, we should know it. In fact, you know that size of a nucleus depends on its mass number. You have studied these things in the nuclear property. In case of a spherical nucleus, you know that the radius of a spherical nucleus R depends on its mass number, and it is given as R equal to R naught a to the power 1 by 3. You know it. So you can see, if mass number A is large, the radius of the nucleus will be large, that is, the nucleus will be of larger size. And you know, inside the nucleus there are nucleons, that is neutrons and protons, and between those nucleons an attractive nuclear force acts. The nucleons attract one another, and that force is called nuclear force, you know, and that nuclear force actually binds the nucleons inside the nucleus. So the nucleus is stable due to the attractive nuclear force. You know it. But you have studied in very detail in the previous lectures that nuclear force is a short range force. Nuclear force is a short range force. It is effective only when the distance between two nucleons, you know, is of the order of 10 to the power minus 15 meter. That is a 1 femtometer. Only then this nuclear force is effective. On the other hand, since the nucleus contains protons and protons have positive charge, and you know the positive charge will repel one another by electrostatic force of repulsion or Coulombian repulsion. So inside a nucleus there are two types of forces. First one is the attractive nuclear force, and the another is repulsive electrostatic force between the protons. And as I have told you that our nuclear force is a short range force, it will be effective only when the distance between two nucleons is very small, that is of the order of 10 to the power minus 15 meter. On the other hand, you know that Coulombian force is a long range force. It means Coulombian force is effective even when the two interacting charged particles are far separated. Even then this force is effective. So if the mass number of the nucleus is very high, that is greater than 210, its radius will be very large, as radius is proportional to a to the power 1 by 3. So in such a heavier nucleus of larger size, actually the Coulombian repulsion is stronger than the attractive nuclear force. You can think the Coulombian repulsion is stronger than the attractive nuclear force, and Coulombian repulsion actually tends to break the nucleus. On the other hand, the attractive nuclear force tends to bind the nucleons. So what will happen? Since the disruptive force, that is the Coulombian repulsion, is stronger than the binding force, that is the attractive nuclear force, so such heavier nuclei will be broken due to the stronger electrostatic force. In this case, actually, the electrostatic force overcome the attractive nuclear force, and so our nucleus get disrupted, that will broken, the nucleons will be actually separated. So such a nucleus have a tendency to break and get stability. So nucleus tends to decrease its mass number. Why the nucleus will tend to decrease its mass number? Because you know, when mass number A will be decreased, its size will be decreased. And when size will be decreased, then attractive nuclear force will overcome the Coulombian repulsion. So such nuclei have a tendency to decrease its mass number to get stability. Are you getting the things? Since the nucleus, the region of the instability of such nucleus is its larger mass number, so to get rid of this instability, the nuclei tends to decrease its mass number. And for decreasing mass number, alpha decay should take place. When there will be an alpha decay, the nucleus will emit alpha particle, then mass number you will see will be decreased by 4. And that's why a heavier nucleus suffers alpha decay for decreasing its mass number and getting stability. Okay? I think you have understand what type of nucleus will suffer alpha decay, why those nucleus suffer alpha decay. All these things have been clear to you, as I hope. Okay? So let us proceed now. How this alpha decay process takes place, I am just going to represent this alpha decay process by a nuclear reaction. You can see. Let us consider that there is an unstable nucleus ZXA. This is called actually parent nucleus. This is unstable. You can see. Its charge number, that is number of proton, is Z, and its mass number is A. If this nucleus emits an alpha particle, that is it suffers alpha decay, then an alpha particle will be emitted. You can see this is your alpha particle, which is simply the nucleus of He4. And so you can see, since the alpha particle has 2 protons and 2 neutrons, so definitely the resulting new nucleus, which is called daughter nucleus, will have a number of protons decreased by 2, and the number of neutron also decreased by 2. So the daughter nucleus has charge number Z minus 2 and mass number A minus 4. Okay? So this equation 1 actually, or you can say this reaction actually depicts the process of alpha decay. And you can see after this alpha decay, we get a daughter nucleus whose mass number has been decreased by 4 and charge number has been decreased by 2, and the number of neutron has been also decreased by 2. So I have mentioned it here that the number of proton Z is decreased by 2, number of neutron that is also decreased by 2, and mass number has been decreased by 4. This daughter nucleus is in fact now a stable nucleus. So due to this alpha decay process, we get a stable daughter nucleus. Okay. For a proper example, you can take the example of this bismuth. Bismuth 83-212. This bismuth, you can see, has a mass number 212, and this 212 is greater than 210. So this may suffer actually the alpha decay process. And when it suffers alpha decay process, we get the daughter nucleus thallium. And thallium has actually the number of protons 81 and mass number 208. You can simply subtract 2 from 83, then you will get 81, and 4 from 212, then you will get actually 208. And this is your alpha particle. Okay. So when bismuth suffers alpha decay process, the daughter nucleus is thallium, and its mass number has been decreased by 4, and it is 208. Okay. So this is a proper example for the alpha decay process. Okay. Now you know, we for any nuclear process or nuclear reaction, we define an energy which is called actually the Q value of the process. Since alpha decay process is also a nuclear reaction, so we will define, or we will calculate what will be the Q value of this alpha decay process. Okay. You know, you have studied earlier that actually the Q value of a nuclear reaction is defined like this: Q equal to Ui minus Uf. And what is this Ui? Actually, this Ui represents the rest mass energy of the reactant, and Uf represents the total rest mass energy of the product. Or in other words, you can say that this Ui is the total rest mass energy of the initial constituents, and Uf is the total rest mass energy of the final constituents. So you can see, I have mentioned it here, that this Ui is what? Ui is rest mass energy of the initial constituents, and Uf is the rest mass energy of the final constituents. Okay. Now see this equation, which I have actually mentioned in this equation 1. This equation 1, which actually represents an alpha decay process. Here there is only one initial constituent, and that is Zxa. Okay. And in final constituents, you can see there are two components of the final constituents. One is the daughter nucleus and another is the alpha particle, that is the nucleus of helium. So you should note what are actually the rest masses of these components. So you can see, as Zxa, this nucleus is the parent nucleus. I have actually considered here its mass is m of Zxa. This is just a symbol. This is rest mass of the nucleus Zxa. And when you will multiply this rest mass by c square, you will get the rest mass energy. According to Einstein's mass energy equivalence relation, you know, if mass will be multiplied by c square, where c is the speed of light in free space, then you get actually the rest mass energy. So the rest mass energy of the initial constituent in this nuclear process will be what? This will be m of Zxa times c square. And similarly, you can find the rest mass energy of the final constituents. In final constituents, there are actually the daughter nucleus and the alpha particle. So I have written here, this is mass of the daughter nucleus plus mass of the alpha particle times c square. Okay. Now, according to the definition of Q value of the process, you know, Q is equal to Ui minus Uf. So we will subtract this UF from UY. And when you will subtract, what you will get? This Q will be equal to m of ZXA minus m of Z minus 2DA minus 4 minus m of 2He4 times Ca square. Okay. So this is actually the Q value of this process. Definitely this Q value of process will be greater than 0 because a nuclear process only takes place without giving energy from outside only when this Q is greater than 0. So definitely the rest mass energy of the initial constituent will be greater than the rest mass energy of the final constituent. Okay. Now you know that if all the masses appearing in this equation 3 are in unified mass unit or you can say in atomic mass unit, and you have definitely studied that one atomic mass unit or 1 U is just equivalent to 931 mega electron volt. It means when you transform a mass of 1 U into energy, you get 931 mega electron volt energy. So if all the masses present in this equation 3 are in U, then you can find this Q value of the process simply multiplying this expression by 931. So the Q value of this process will be what? M of ZXA minus M of Z minus 2 DA minus 4 minus M of 2He4 times 931 mega electron volt. Remember, in this equation 4, all the masses appearing in this equation will be in atomic mass unit. Then you simply multiply by 931 and you get the Q value in mega electron volt. Okay, this is a very simple concept, and this is very simple but very important for competitive examinations. In competitive examination, you will be asked to find the Q value of a nuclear process or particularly the alpha decay process. All the masses will be given and you have to simply put that formula and put the numerical value and you will get the Q value. Okay. Now, the Q value of the process is the energy evolved in this process, and that released energy is actually shared by the disintegration products. And you can see in this alpha decay process there are two disintegration products. One is the daughter nucleus and another is the alpha particle. So the Q value of this process, which is actually also known as disintegration energy, that energy actually appears in the form of the kinetic energy of the daughter nucleus and the alpha particle. It means Q will be divided in two parts. A part of this released energy Q is shared by daughter nucleus in the form of kinetic energy. The remaining part is shared by the alpha particle in the form of kinetic energy. So now we will find how much energy is shared by the daughter nucleus and how much energy is shared by the alpha particle after this alpha decay process. You will see that the energy shared by alpha particle will be much greater than the energy shared by the daughter nucleus. Due to larger mass, this daughter nucleus will share a little amount of energy, and due to a smaller mass, this alpha particle actually shares the most of the part of the Q value of the process. In fact, this calculation can be done by simply applying the principle of conservation of momentum and principle of conservation of energy. In fact, in any nuclear process, the several conservation principles are valid, and we solve the problem of nuclear decay by applying the principle of different conservation principles. So for calculating how much energy is shared by alpha particle and daughter nucleus in the form of kinetic energy, let us consider that Kd is the kinetic energy of the daughter nucleus. It means this much energy this daughter nucleus actually gets after this disintegration process. And we also consider that this K alpha is the kinetic energy of the alpha particle. Since Q has been divided in two parts, one part of Q appears in the form of kinetic energy of daughter nucleus, another part of Q appears in the form of kinetic energy of alpha particle. So definitely, according to energy conservation, this Q will be equal to Kd plus K alpha. Okay, this is a very simple fact because Q has been divided in two parts. One part is the kinetic energy of daughter nucleus and another is the kinetic energy of alpha particle. So when you will add these two parts of energy, that is Kd and K alpha, you will get simply Q. Okay. Now, we consider that our parent nucleus, this is your parent nucleus X. We consider that before this alpha decay, this parent nucleus was at rest. This was at rest. And if it was at rest, its initial, if it is at rest, its momentum will be equal to 0. Momentum of the parent nucleus will be what? 0, because we consider that before this decay process, our parent nucleus was at rest. And after the decay process, you can see there will be the daughter nucleus D and the alpha particle. And both of these will actually move. So, you know, in any decay process, the total linear momentum of the system remains constant. So, before decay, the total linear momentum, and after decay, the total linear momentum of the decay of the colliding systems will be same. Before decay, there is only one component of this system, that is the parent nucleus. So I have written here the initial momentum as Px. This is momentum of X before decay. And after decay, you get daughter nucleus and alpha particle. So after decay, the total momentum will be Pd plus P alpha. Pd means linear momentum of daughter nucleus and P alpha means linear momentum of alpha particle. Okay. But as you have assumed that the parent nucleus is at rest before the decay, so this Px will be what? This will be 0. Okay. And Pd and P alpha I have assumed at is, so this is Pd plus P alpha. So you can see Pd will be equal to minus P alpha. What does it mean? It means that the linear momentum of alpha particle and the linear momentum of the daughter nucleus both will be same in magnitude, but this minus sign implies that their motion will take place in the opposite direction. So if you consider that our alpha particle starts moving in right direction, this nucleus will recoil in left direction. Okay. So Pd is equal to minus P alpha, but magnitude of these two momenta will be same. So we have you can write that magnitude of Pd, that is Pd is equal to P alpha. And since both are same, so I have assumed that this Pd and P alpha is equal to P. It means Pd and P alpha both are same, so I have written here P for both of them. Okay. Now, you can find the value of Q now. Since you have seen that Q is equal to Kd plus K alpha, and you know kinetic energy of a particle having linear momentum P is defined as K equal to P square by 2m. You know, this is classical formula for kinetic energy. So kinetic energy of daughter nucleus. What will be this? This will be PD square over 2md. md means this is mass of the daughter nucleus. And similarly, K alpha, this will be P alpha square over 2m alpha. Here m alpha, I have assumed this is mass of the alpha particle. But you have seen that PD and P alpha both are same. So PD and P alpha have been replaced by simply P. So this is P square over 2md plus P square over 2m alpha. Now you can take P square over 2 as a common factor. So you can write Q is equal to P square over 2 times 1 over md plus 1 over m alpha. Okay. Now take the LCM, and after taking LCM, you will get that Q is equal to P square over 2 md plus m alpha over m alpha into md. And so from here you can calculate the value of P square, and this P square will be what? This will be 2Q times m alpha md over md plus m alpha. Okay. Now once you get the value of P square, now you can find the value of K alpha and Kd. You can see K alpha is what? K alpha is P alpha square by 2m alpha, but you have seen that P alpha is simply equal to P, so K alpha is equal to P square over 2m alpha. And when you will substitute the value of P square from this equation 7 here, you can see this 2m alpha will cancel out, and after this cancellation we get that K alpha is equal to md over md plus m alpha into Q. Okay. So this is kinetic energy shared by the alpha particle. Okay. And similarly you can find Kd. Kd will be P square over 2md. So then when you will put the value of P square from this equation 7, this 2md will cancel out, and your result will be m alpha over md plus m alpha times Q. So these are actually the kinetic energy of the alpha particle and the daughter nucleus after this alpha decay process. Now you can express this kinetic energy in terms of mass number of the parent nucleus. You can express it. How? You know, in fact, mass of a neutron is slightly greater than mass of a proton. You have an idea. In fact, when you write the mass of a neutron in terms of the unit of energy, then this is 939 mega electron volt per c square. This is mass of neutron. And a mass of a proton, this is 938 mega electron volt per c square. So you can see that neutron is slightly massive than a proton. But in a rough calculation, since the mass of neutron and proton are very close, the difference between these two is very small. So in general calculation, we simply neglect that a smaller difference of masses of the neutron and proton. So in this calculation, we simply consider that mass of a proton is almost equal to mass of a neutron. We consider it. Okay, almost equal. So in this condition, you can take m as mass of a proton and also mass of a neutron. So in this condition, what will be the mass of a daughter nucleus? Mass of daughter, you have seen the daughter nucleus has mass number A minus 4. A mass number means what? Mass number simply represents the total number of nucleons. So daughter nucleus contains A minus 4 nucleon, and mass of one nucleon is m. So mass of one nucleon is m. So mass of A minus 4 nucleon will be what? This will be m into A minus 4. So roughly you can say that mass of daughter nucleus is almost equal to A minus 4 into m. And again, mass of alpha particle. You can see mass number of alpha particle is what? For alpha particle, mass number is equal to 4. So, and mass of one nucleon is m. So, mass of 4 nucleons will be 4m. So, mass of alpha particle, you can write this is equal to 4m. So, now you can put the value of this md and m alpha in this equation 8 and 9, and then you will get k alpha and kd in terms of the mass number. So you can see at the place of md we have written a minus 4 into m, and see the denominator. In denominator there is actually md plus m alpha, but md plus m alpha mass number will be what? A minus 4 plus 4, that will be equal to simply A. It means this is just mass of the parent nucleus. So in denominator the total mass will be A into m. Now this m and this m will cancel out, and you can say that this k alpha, here also you should write approximately equal. So this k alpha is approximately equal to a minus 4 over a times q. You should remember this formula, because this formula will be very helpful in solving the numerical problems. Okay. Similarly, you can find the value of kd from that result, and you can also find the value of kd now independently in this manner. Since kd plus k alpha is q, so you can write kd equal to q minus k alpha, and k alpha is this much. So we will simply subtract the value of k alpha from q, and that will be what? Take q as a common factor. This will be 1 minus a minus 4 over a. Taking LCM, you can see kd will be equal to 4 over a times q. You can see since a is definitely greater than 210, so in this case a minus 4 will be much greater than this 4. And if a minus 4 is much greater than 4, you can say that kinetic energy of alpha particle is much greater than kinetic energy of the daughter nucleus. So most of the part of disintegration energy Q, the alpha particle shares the most of the part of energy. The daughter nucleus, due to its heavier mass, shares a little amount of energy. More or less you can say almost all energy is shared by this alpha particle. So what will be the Q value of this process? What amount of kinetic energy will be shared by alpha particle and daughter nucleus? All these things you have seen, and I hope you have understand this calculation, because this is a very simple calculation. As I have told you earlier, this is just an elementary lecture on alpha decay, but in forthcoming lecture we will see a rigorous theory of alpha decay, which is called actually the Gamow theory of alpha decay.